Great. Sorry about all the technical issues. So I'm going to talk about this theory of classical gravity and its joint work with some of my students, in particular Isaac Layton, Mohammed Sajid, Barbara Skoda, Andrea Russo, and Zach Willer-Davies. And it's a few publications we've put up in the last while. And the general idea is a kind of a very simple question. The question is, we have, quantum theory, we have classical mechanics, and the question we're interested in is it possible to combine these two frameworks and in a consistent manner? And we already know partly how to do it. For example, if we have a classical potential which influences a quantum system, like a particle in a box or a double slit experiment, then we can do that just fine. The problem is with the back reaction. So if we have a quantum system and it back reacts on a classical system, we don't know how to deal with that very well. Can people hear me all right? I noticed there's a bit of noise in the background. Okay, good. And the motivation is twofold. One is, well, from a practical point of view, there's often we often have a system which we want to treat classically. So this is the case in cosmology, for example, or in black hole evaporation. We always treat the background space-time classically. So from an effective point of view, we're interested in this limit or understanding this combination. But I think it's reasonable to also think, to ask the question whether it could be the correct fundamental description instead of a quantum theory of gravity. And the reason, well, there's a few reasons for this. So can people see my pointer now if it's on the screen there?
The pointer, I don't see any.
Yes, a bit small, but
a very small one. Could you please increase it, or this is a very, very small.
It's very small.
Small dot, maybe arrow, very small. Yes.
Okay.
In fact, if there is a possibility.
Yeah, it doesn't seem. Use mouse pointer as pen P.
Zoom
I can do this thing where I like do this.
Oh yes.
Okay. So
yes, you can make annotation. Yes.
Yes. So the first thing is that the space-time, the classical space-time, gives us a causal structure, and when we define the quantum field theory, often in terms of commutators, then we need this causal structure. I don't know really how to define a quantum theory without this background causal structure. The second reason is that I would say that the other forces in nature are very different from gravity. So gravity is the only one where we have this universal in which all other fields live. There's no other forces of nature which give us this universal geometry. So gravity seems to be special in this particular way. Other gauge theories, you have this internal gauge degree of freedom, whereas gravity is instead this universal geometry, as I said. So it's the gauge degree. It's not a gauge theory like other theories, and I think it's not unreasonable to think of it like we have these gauge, these gauge fields where we exchange gauge bosons in order to have an interaction between two systems, and that these live in a background space-time, which we need to treat classically. The other reason why we might think of well, the two other reasons why we might think that gravity is special is that when you try and quantize gravity, you get this Wheeler-DeWitt equation here, which essentially tells us that the solution is a stationary state, and that seems very strange, and we don't really yet know how to understand that. So the Wheeler-DeWitt equation might be telling us that it's not correct to quantize gravity. And then, of course, the biggest thing is that as soon as when we try and quantize gravity, we find that it's not renormalizable. And so those are the reasons why we might want to think of perhaps gravity as being classical, not just from an effective point of view, but also from a fundamental point of view. Are there any questions at this point? So let me just say that I try and adopt an agnostic position to this question. I think it's a reasonable question to ask, whether we should be quantizing gravity. And I would say that if it's true that gravity is, that space-time is somehow classical, then there's a whole bunch of interesting consequences which emerge. One is that the theory becomes renormalizable and without ghosts. And those of you who are interested in quadratic gravity, I think this will be of interest to you. One of my motivations was the black hole information problem. I tend to be of the view that we get into a paradox unless black holes destroy information, and so this theory provides a way for information to be destroyed in a consistent way, which is difficult to do in a quantum theory. The other reason is that we find that we don't need the measurement postulate of quantum theory. We automatically get that if you have a classical system which interacts with a quantum system, then the quantum system will become classical. So you get for free collapse of the wave function in some sense. This proposal is experimentally testable. And there's also some interesting implications for the cosmological constant and dark matter. So when I used to give this talk a couple years ago, has been this big, huge debate about whether it's possible to find consistent dynamics between classical systems and quantum systems. So indeed, that's true. There has been a debate for quite a long time, ever since Feynman in the 50s. But I think that debate is more or less settled now. We know that consistent dynamics can exist. There's even been particular examples in the mid-90s of particular theories. And so we know that we can consistently couple classical systems and quantum systems. And there's already been a slew of experiments which have been proposed to try and test these theories. Okay. The one thing I want to emphasize here is that often when people think of classical and quantum, classical theories of gravity, they think about the semi-classical Einstein's equation, and I don't. So this is not equivalent to the semi-classical Einstein equation, and therefore it doesn't. Those of you who know the semi-classical Einstein equation will know that it has certain pathological properties when fluctuations are large, at least, and the present theory does not have those issues. So that's what I want to say. And so what I'm going to do, the plan for this talk is the following. I want to tell you describe what the most general form of classical quantum dynamics is. I will then talk about how we can use something called the decoherence versus diffusion trade-off to test this theory. And then we can talk about renormalizability, but without ghosts. And also, if I have time, we can talk about how this diffusion gives a sort of entropic force and can look like dark matter and dark energy. So that's the plan for the talk. Are there any questions so far? Okay.
Oh, please just continue.
Okay. So I'm partly asking because I do really encourage it. It will help me. So
here is the question.
Okay, okay. Please.
You mentioned Feynman, and I remember
Yes.
reading his book on quantum gravity, right, where he discussed about quantization of gravity and so on. So he made these two slight experiments when the classical gravity involved. Are you going to discuss this? There was a very beautiful discussion of him.
Yeah, let me discuss it. Actually, let me discuss it first.
It was very tiny questions of interaction of when you have a classical gravity and quantum system with a wave function going through this slits and
slits.
Yes.
Yeah. So can people see the slide that I've just put up there? where we have
Hi, Jonathan. May I ask something?
Sure.
Yeah, so you mentioned about semi-classical gravity and saying that this is not semi-classical gravity.
Yes.
So I just wanted to make sure, like, if I want to treat geometry classically and the other fields quantum mechanically, is there something wrong with this equation? Like what you write, G mu nu equals to expectation of T mu nu as you write in semi-classical gravity? I didn't understand that point.
Yeah, so you know what, so let me answer both of those questions. And let me start with this semi-classical gravity, and then I'll start with the Feynman, and then I'll go to the Feynman argument. So let me just go back up. Ooh, no, I'm going the wrong way.
Okay.
Let me start with the Feynman argument.
Maybe, Jonathan, maybe you follow your presentation systematically, because if you will jump
I'm actually,
now
yeah,
to
I'm
the end of your talk,
yes,
it would be
that's okay. That's okay.
time.
I actually prefer this. So
Yes.
So let's first discuss the Feynman argument, because it's very beautiful, and it will, and then I'll discuss the semi-classical equations. And so let's discuss the Feynman argument. So the Feynman argument, this is actually a variation of this due to Yakir-Aronoff, which I think is a bit more precise. And so the argument is as follows. We take particles, like heavy particles, they could be gold atoms, it could be the moon, and I interfere them in an interference experiment. So I imagine, can people see my slide of the interference experiment?
Yes, we can see, but we pointed too small, but it's okay.
Okay, so we have this interference experiment, and now we can imagine that someone sits there with a pendulum. So here's the pendulum, and here's LIGO out there, or Lisa, and it's going to look for, try and measure the gravitational field to determine where this particle is. And because if the gravitational field is classical, then I will be able to measure the gravitational field to arbitrary accuracy. And if I can measure the gravitational field to arbitrary accuracy, then I can figure out where the particle is. And I will know, for example, that it went through the top slit rather than the bottom slit. And if I can figure out that it went through the top slit rather than the bottom slit, then I will be able to determine which slit the particle went through, and there won't be an interference pattern. So that's the Feynman-Aronoff argument. Is that clear for people?
I think it is clear.
Okay. In other words, a classical field you can measure to arbitrary accuracy, and so you can use it to determine which slit the particle went through. But there is an assumption in this argument, and the assumption is that the gravitational field is deterministically produced by the particle. So, for example, if the particle is coming from the top slit, then the gravitational field should tell you exactly where the particle is. And that's an assumption, let's call it the deterministic assumption. And so if I'm willing to part with, if I'm willing to have a breakdown of determinism, then this argument doesn't have any force. And so here in this theory, the gravitational field has a stochastic component, so it fluctuates. The gravitational field fluctuates, and if the gravitational field is fluctuating, then measuring the gravitational field doesn't determine precisely which slit the particle went through.
Why do you assume that gravitational field is stochastic?
So what we can do is we can actually derive the most general form of an interaction between a classical gravitational field and a quantum system. And we find that it can only be mathematically consistent if the gravitational field is stochastic. So it's not an assumption, rather it is a consequence of consistently coupling quantum systems with classical systems. And I'm giving you this kind of Feynman-Aronoff argument, which you can use to see that the only way you could consistently couple a quantum system with a classical system is if there is this random stochasticity in the classical degree of freedom. And the reason is that if there wasn't, if the gravitational field wasn't stochastic, you would be able to determine which slit the particle went through. by measuring the gravitational field, and then you would not have any interference pattern. Does that make sense? So here's a schematic. I can imagine that the gravitational field here is produced, if the particle goes on the left slit, then there's one gravitational field. If the particle goes on the right slit, there's another gravitational field. If those gravitational fields are produced stochastically, then there's a whole bunch of different gravitational fields produced, and they might have some overlap, and measuring the gravitational field, therefore, does not allow me to distinguish whether the particle is it went through the left slit or the right slit.
Sorry, Jonathan, I also have a question.
Yeah.
So, I mean, if gravity were quantum, you would still have some, of course, kind of fluctuation,
Yes.
some stochastic processes that would still basically allow you to not determine where the particle went through. Okay.
Yes.
And in that case, you would know that the origin is quantum. But in your case, what would be the origin of this type of stochastic behavior?
Yeah. So there's no origin. I mean, in some sense, it is just that the gravitational. You need these stochastic fluctuations in order for the theory to be consistent. So as soon as you treat space-time classically, you have to have these. It has to fluctuate stochastically. My way of thinking about it is that there is no origin to these fluctuations. That's probably an unpopular opinion. I think as physicists, we want to ascribe a hidden environment to that. I'm not sure in this case that you can do that, for the same reason that in a collapse of a quantum system, we treat whether the particle is spin up or spin down as a random happening, and we do not believe. I mean, you might believe that is not a random process, but I don't know how to think about it in any other sense except that it's a random process.
Can you refer this Dirac-Zitterveregung?
Sorry, Dirac-Zitterveregung.
He was discussing. Then he discussed the Dirac equation. He formulated this alpha you can average, and you see that there is a how to say zigzag motion, which is in German is Zitterveregung. This random fluctuation.
Yes.
So that will produce probably gravitational field fluctuating, right? If the particle is going as a zigzag, right?
Do you mean in the quantum? Do you mean in the quantum case?
Yeah, if you consider the quantum theory of electron.
That's right. So, okay. So quantum, the vacuum, of course, has quantum fluctuations as well. The difference is that in the double slit experiment, what actually happens is that the fluctuations just don't need to be as large in the quantum case. In fact, they're very small and they're very hard to measure. We don't measure vacuum fluctuations very easily. Whereas if you have a classical theory of gravity, the fluctuations actually have to be very large and potentially measurable in the lab. And the reason is to do with this fact that if you can measure the gravitational field, you will determine which slit the particle went through, and you won't disturb the gravitational field. On the other hand, in a quantum gravity theory, you could also measure the gravitational field to determine which slit the particle went through, but you would completely disturb the system. So you don't need a lot of stochasticity in the quantum case in order to still have interference patterns, whereas in the classical case you do. So that's the main difference between the two cases.
Okay, please ask your question.
Yes. Jonathan, Chandrasekhar's calculation of the stability of white dwarfs interplays classical gravity with the quantum mechanics of Pauli degeneracy of the electrons. And it seems to give a mass that fits observation.
Yes.
Does that mean that these stochastic effects you're describing just simply are not relevant for a white dwarf?
Yeah, I would. So these stochastic fluctuations, you can measure how big they need to be, and they don't need to be very big. And so we don't expect it to be relevant in comparison to the very large gravitational fields that we have on Earth or in a white dwarf or in our solar system. So that's why you don't expect any changes to solar system tests of gravity. So these fluctuations are very small, but they need to be big enough so that you can't determine if the electron is here or there. So they only need to be, the gravitational field produced by an electron is tiny. And so you need the fluctuations to be large enough so that you can't tell where the particle is. And that's very small.
Okay.
Maybe I'll give the argument again, but in a slightly different way. So imagine we have this, as I said, the superposition, say, of a gold atom. So the gold atom is either here or there, if people can see my screen. And now if the particle is here or there and we turn on the gravitational field, then the gravitational field will bend space, space-time will be bent in a different way depending on whether the particle is here or there. And so by measuring the gravitational field, we should be able to determine whether the particle is here or there. And so, this is another way of interpreting Feynman's argument, which is that if the gravitational field is classical, it'll instantly collapse particles to being here or there. Is that clear?
Can I make a short comment?
Please.
So this well-known paper by Einstein and Rosen on particle problem in general relativity, and they clearly state in the context of gravity, you do not have clearly a particle notion. It's all quantum fields. So, you have
sure, and
that your particle notion still exists when you have gravity, but this conflicts with all the things we understand about quantum fields and quantum field theory in crowd space-time.
No, I'm not. So of course, on a fundamental level, these are just fields. Of course, but I mean, we do think, we do see electrons. They do exist in superposition, and of course, we know that they are just fluctuations of the electromagnetic field. But if you want, I'm using the placeholder particle. If you want to replace particle with fluctuation, with a configuration of the electromagnetic field such that it behaves like a particle, you are welcome to do that. But as a placeholder, I'm just going to use the term particle. But of course, fundamentally, these are just fields.
Yeah, your previous comment is about when you have a particle here and there, and you add gravity, and then you say that your wave function collapses.
That's right. So here imagine that I have a config, I have a superposition. Even in field theory, I can think of a superposition of field configurations which are localized, which are in a superposition of being in different places.
Okay.
I don't think that.
Anyway, my confusion is localization is not possible when you consider the fields.
No, these are, of course, are way, well, it's also not possible if you consider particles, but yes, these are, of course, have a distribution. Yeah, I mean, let's just use particle as a shorthand for a wave packet of a field configuration.
Okay, thanks.
Okay. So I have this particle, which is in a superposition of here and there. I turn on the gravitational interaction. The gravitational field is classical, and the danger is that I can measure the gravitational field with arbitrary accuracy without disturbing it and determine whether the particle is here or there, and so automatically collapse the particle. But if you have stochasticity, so if the gravitational field has some fluctuations, and so here are my fluctuations, then measuring the gravitational field will not determine whether the particle is here or there, right? Because we have these fluctuations, and so we can measure the field, but we can't use it to uniquely determine where the particle is. And so if you have these fluctuations, then you can still have a particle which is in a superposition of here and there. And so let's imagine that we have some level of stochastic fluctuations. Well, we have these stochastic fluctuations, but we can keep monitoring the gravitational field. So we measure a little bit the gravitational field, and we, even though we have stochastic fluctuations, if we measure the gravitational field for a long enough time, eventually we will be able to figure out that the particle is there and not here. Oh, sorry. Is that a question? Sorry.
No, please continue, Jonathan. There was someone unmuted.
Okay, so does that make sense? So I somehow am able, you can see that you need these stochastics, and the larger the stochastic fluctuations are, the longer you can have a particle which is in superposition. Are there questions about that?
Yeah, can I ask a question, Jonathan? Sorry.
Mm-hmm.
Okay.
Yeah.
So you basically you're saying that so the stochasticity of gravitational field can preserve somehow superpositions, but then it means that in a sense in this kind of approach there is no space, let's say, for gravitationally based collapse models. Just like, I don't know, I'm thinking of Penrose model or.
Right. Well, so you end up getting a different form of both a different form and maybe a different mechanism. So you do get collapse in some sense. It's of a different form to the Diochy-Penrose one, and so in particular, what we find is that the quantum state is pure the whole time. So I don't know if I have a picture. Yeah. So if you see here, what happens is that the quantum state stays pure and collapses to, say, in this case, either being, say, on the left or on the right. It collapses, but it stays pure as it does that. So it's effectively slowly moving from being in a superposition to being on the left or being on the right. And it does that while staying pure the whole time. So in some sense, it's only a decoherence when you trace out the gravitational field, but the quantum state stays pure the whole time. Did that?
Excuse me. So
Yeah.
let's start from the beginning. So what is your general scheme? You assume that you have some manifold, space-time manifold. In this space-time manifold could live some quantum field and gravitational field, some stochastic field. Is correct or not?
Because, yeah, I think so. Yeah.
Is it correct?
Yes.
Okay.
I'm not sure I caught it completely, but.
So your idea, instead to quantize quantum gravity more or less as a usual case, you prefer to discuss only stochastic processes related with gravitational field.
That's right. So you have a classical manifold. So you have a classical space-time manifold. It stays classical. It interacts with, so you have a back reaction of the quantum fields on the classical manifold. And in order for that to be mathematically consistent, you need that there has to be, that coupling has to be stochastic, that there has to be some noise in the gravitational field. And as long as the coupling is stochastic and is not a deterministic theory, then the theory is mathematically consistent and also has some advantages like renormalizability and giving you collapse of the wave function.
Okay, okay, please continue.
Okay. So what I would do now, I can go through the formalism a bit if people are interested. It's a little bit technical. I could also mention, maybe briefly mention, so because someone was interested, this is the semi-classical Einstein equation, which people often use, where they say, okay, we have G mu nu on the left, it's classical, T mu nu is on the right, the stress energy tensor, so we need to, it's an operator, and in order to make it consistent, we need to take the expectation value. The problem with that is that if you have, say, a particle which is in a statistical mixture of being on the left or the right, like a moon, a planet which is on the left or on the right, then when you take the expectation value of its stress energy tensor, it's the expectation value of half a planet on the left, half a planet on the right. And if you drop a test particle, it'll go down the middle, and the two half moons will attract to each other. So the semi-classical equations, which is what people often use to discuss gravity in the classical limit, that is somehow not appropriate. And leads to certain pathologies. Whereas this method I'm going to mention, which uses a master equation or a path integral, is mathematically consistent. Good. So let me discuss the mathematics of it. We have a quantum system, so we have quantum mechanics, and we have also a classical system, and so the quantum system, we have the Heisenberg equation of motion, which is like the Schrödinger equation, but for a density matrix. And for the classical system, we have the usual Liouville equation. And now our system is represented by a in phase space. So we have a Q and a P. That's the classical system. So we have a point in phase space here. And then conditioned on being at that point in phase space, we have a pure quantum state, for example, a two-level system. So we can represent this like if Z is the point in phase space, then we are at a particular, we have a probability distribution of being at a particular point in phase space, Z, and given that we're at that point in phase space, we have a 2x2 density matrix. Is that mathematical formalism clear? This is how we represent a classical object interacting with a object. So for example, I sometimes like showing how we talk about quantum mechanics, how we talk about classical mechanics, and how we talk about the combined classical quantum mechanics, because formally everything looks very similar. So in quantum theory, we have a Hilbert space, we have a density matrix, which is a positive matrix with trace 1. That's how we represent quantum states. Classical states, well, they live in a phase space. Again, we can represent the state of a classical system by a density over phase space. And it is also, like in quantum theory, it's a positive distribution and it integrates to 1. So density matrices and phase space density functions are very similar. Oops. And likewise, we can represent the classical quantum system as the combination of the two things. So we have a probability of being at a point in phase space. So we have this density, and then we have this density matrix, which is conditioned on the point that we're at in phase space. And it also has to be a positive matrix, and it also has to be normalized. So if we take the trace of it and we integrate over phase space, then it has to be 1. So that essentially is all you need, because now you just say that I am allowed to have any dynamics which preserves, which maps states to states, right? So if I start off in some initial valid classical quantum state, then it should be mapped to another valid classical quantum state. And from there, you can derive the most general form of dynamics. Is there a question about how we think about classical quantum states and how we, and just about the idea that there can be a general form of the dynamics which is consistent?
I have a question in relation to this formalism. So,
okay,
basically, I mean, in relation, for example, I hope you're familiar with this Stravinsky's stochastic approach to inflationary quantum fluctuations. So the stochastic approach reproduces exactly the calculation from quantum fluctuations, where you quantize with QFT in curved space-time. So I'm wondering if there is something similar you are doing, or it's totally different. So in your stochastic approach, so
it's a good question. So so let me just say there are quite a few things that go under. So Bela-Hu, for example, has a program of stochastic gravity. There's John Moffat has the various stochastic theories. This is different in both motivation and in the form of it. So it's motivated. It's motivated by just if I have a classical, if I think space-time is classical, this is the dynamics you get, and the form of it is quite different. But they both have, there are other theories which have various kinds of stochasticity. In terms of relating to Stravinsky, the only thing I can say is that so Stravinsky inflation, you have this R squared term, and we also have an R squared term, and because with Sterbinsky inflation, it's the one that's most favored by the experimental data. I think this gives some hope that one can have Sterbinsky inflation. So that's all I can really say about that. Whether that's true or not, I'm not sure. One has to go through the calculation, but on the surface, it seems that it does allow for Sterbinsky inflation.
Okay, thanks.
We are at the 45-minute mark, and I'm not sure I could give so what I would normally do now is talk about the different path integrals which are valid, which have both the quantum degrees of freedom and the classical degrees of freedom. When I talk about renormalizability, I mostly talk about the classical part by itself, and maybe I will jump to that if we're trying to finish on the hour. Is that where what we're aiming for?
We started 10 minutes later, so in principle.
Okay. Okay, so let me go a little bit slowly, and feel free to ask questions. What I'm going to do is I'm going to go through the different kinds of path integrals that we get in quantum mechanics, in classical mechanics, and in the classical quantum mechanics, because they can all be formulated in a very way in terms of path integrals. So you are used to the path integral for quantum systems. I'm computing an amplitude. That's very important that we're computing an amplitude. We want to compute the amplitude to go from some configuration psi I to some configuration psi F. And what we do, we integrate over all paths and we weight them by the action, all right? Now, what I want to do is compute not just the amplitude, but a density matrix. So I want to have both the bra and the ket field. So I start off in some initial state, but I write it as a density matrix. So I start off in a state with psi I, and I want to now compute the final density matrix, and that involves looking at all the matrix elements, both the row and the column. So I've somehow doubled. I'm not just computing an amplitude, I'm computing a probability, but also all the different off-diagonal matrix elements. And so when I do that, I'm in some sense doubling the number of degrees of freedom. And so I have a bra field, which let's call it phi plus, and a ket field phi minus. And so I have an action for the bra field and an action for the ket field, which is complex conjugate. And this is how I can compute a density matrix in the quantum formalism. And this is sometimes referred to as Schwinger-Keldysh formalism or Feynman-Vernon formalism. But it just involves thinking about a bra and a ket field. Are there any questions about this funny density matrix way of thinking of path integrals where I'm looking at it, not just an amplitude, but a density matrix? Okay, so this is how I would do it. And if I have decoherence, then what Feynman and Vernon say is that you should add this decoherence term. And what this decoherence term does in, say, an open quantum system is that it decays diagonal elements. So the diagonal elements, which is when the bra field equals the ket field, this is the decoherence functional, it's 0. But when the bra field is different to the ket field, then these are suppressed and exponentially decay. So if people are familiar with Lindblad equations, this is like the path integral for a Lindblad equation. But essentially what it does is it allows for decoherence of off-diagonal terms. And I talked earlier about the decoherence versus diffusion trade-off, and this is giving you the decoherence part. So it's telling you that states will localize, they will decohere and become localized. Question?
Sorry, Jonathan. So basically you said that this is equivalent, let's say, to a Lindblad master equation. But since I'm not familiar with the Feynman-Vernon formalism, is also there implicit or somehow hidden the assumption of, I don't know, the Markovianity or Born approximation to get the expression, or it's
Yes.
somehow.
So yeah. So here we're talking about Markovian master equations, and if you want to see that it's equivalent to the Lindblad equation, then you can look at this, because this is like the jump term here, because you have an operator on one side and on the other side. Like this is the bra field and this is the ket field. So it's like having an operator on the left and an operator on the right. And then you have the two no event terms, and that can just be written like this. So this is very much like a Lindblad equation. And indeed, we are assuming that there is no memory out there. And the reason we're assuming that is because we're interested in a fundamental theory where one doesn't expect there to be a memory if we're going to treat this as a fundamental theory.
Okay, no, because I was also wondering, since you said that at some point you also apply this to black holes, or in principle to regimes where we have strong gravity, isn't this maybe a bit restrictive in a sense, because it's not the most general, let's say, master equation you can write, but you did some assumptions on the way. So is it still...
So the assumptions are very weak. So if the coupling constants are constant, then that represents Markovian dynamics. If you are allowed to, if the coupling constants depend on time, then you get then that can be give you a non-Markovian dynamic. So there's only, in some sense, there is one assumption. It's very technical. It's to do with some kind of microscopic reversibility. It's in the PRX paper, it kind of gives that assumption, but the assumption is actually very weak. But in a fundamental theory, we take the coupling constants to be, actually constant, and so that is like it's equivalent to a Markovianity assumption.
Sorry, maybe very naive questions. I was trying to understand physical meaning of plus and minus.
They're just the bra and the ket field. So you can think of it as they just, they're in a quantum system. If I want to describe a density matrix, I just have more degrees of freedom than if I have if I'm just care about the amplitude, right? So I need to double my degrees of freedom. So it's the same field. The phi plus and the phi minus represent the same physical field, but they just represent the bra and the ket. Just like when I write a density matrix, it's like I'm doubling. I have two copies of the quantum state. It's the same system, but I'm just doubling the number of degrees of freedom because I'm representing it as a density matrix.
Okay.
So, Jonathan, maybe one last question about this slide, if I can. I'm also not familiar with this Feynman-Bernoulli formalism, but if I look at the sign in the action, like the first term as a plus sign, the second term as a minus sign, does that mean that the plus field and the minus field, they have opposite sign in the kinetic term? Compared the two?
No.
I mean, so in the one case, so the reason that you have the plus sign is because in the one case you're computing this amplitude, and the other one you're just computing the complex conjugate.
The complex conjugate, no, I understand that. So,
yeah,
but if you want to derive dynamics, like for instance, some propagator from there, will you get the minus sign inside? Or?
Well, yeah, but its interpretation is different, right? So you're computing the different amplitudes. It looks a bit funny if you're not used to it, but there's no you don't have any instabilities or anything like that. That's what you're
okay.
about.
I see.
You just have to interpret it. I mean, in some sense, it's going. I mean, you could say it's going backwards in time, maybe, or something. But
I see.
That's maybe not. I would just think.
No, I see. I see the point. I see the point.
Yeah. Okay.
Yeah. Thank you.
Now, classical path integrals. We don't talk about classical path integrals much because there's only one path. I have to follow the Hamilton's equations, and so I have a delta function around Hamilton's equations, and so I'm allowed all Q's and P's which satisfy Hamilton's equation, and there's only one path. So classical path integrals are boring, except if you are allowed to have some stochastic noise. So people are probably familiar with like Brownian motion or the Langevin equation, but this is essentially a way of talking about Brownian motion, for example. There's actually a nice chapter in Feynman and Hibbs about it. It's called the Onsager match loop. path integral or MRS. But you effectively what you have is you have here Newton's law, so F equals ma, right? And you allow stochastic fluctuations around the constant force. So I have the force, but I have fluctuations which are allowed, but they're suppressed exponentially by this minus sign in the path integral. So, you have more degrees of freedom because I can tell you I can start off with an initial position, an initial velocity, and an initial acceleration. And then this path integral says, okay, well, mostly you will have this standard force, this deterministic force, but I have these little fluctuations, as in Brownian motion, around in the acceleration, and those are allowed, and they give me different paths, and the probability of those different paths are weighted by this path integral. So here's the action. It's like an equation of motion squared, and then with a minus sign. So I have some equation of motion, I square it, and then that if I satisfy the equation of motion exactly, then that's the preferred path. But there are all kinds of other paths which also contribute, except that they're suppressed. And of course, you can see here that this d2 here is the diffusion constant, and the smaller the diffusion constant, the more I disallow paths which deviate from the deterministic path, but I do allow some of them. So this is this Onsager-Matchlieb path integral. Is that clear, this Onsager-Matchlieb path integral? This will be, I think, the important thing, and I'll mention then quadratic gravity. So this is, if you're interested in this kind of connection with quadratic gravity, this might be the time to ask any questions about this equation of motion squared path integral for Brownian motion.
For me, the subject is, and your proposal is unclear, but maybe you can kindly proceed, and maybe we will see your final result, and then we can discuss.
Okay.
Because for me, I'm sorry, for me, the main problem, we do not have the unique quantization procedure for any classical system. But for simplest classical system, we know how to quantize them. But you propose, instead of quantization, to use a stochasticization. Is this procedure unique? What is, if not unique, what is, how you can describe different possibility, what is relation between different stochasticization procedure, and so on. So, but let's see your final result. Maybe then it will be the situation, it will be more clear. Sorry to interrupt you. Please continue.
No, that's a good intervention, because I think it's a very observant statement that rather than quantize the gravitational field, we are stochastizing it, and that allows it to be consistent. And the key thing about making it stochastic is contained right here, where the action is like an equation of motion squared. And so you allow for stochastic fluctuations away from the deterministic equation, but they're suppressed. So here you have, for example, the Euler-Lagrange equation. You square it, and that's your action now. And so the action prefers solutions of the Euler-Lagrange equation, but it allows for deviations, and the strength of those deviations are governed by this D2.
But this is something very different from usual situation, because if you look on your first integral, you get q with two dot and square. This is a third order of derivative. This is the origin of ghosts, usual ghosts.
Good.
Exactly.
Okay.
How you deal with all this stuff?
Yes, good. So you're prefacing what we're about to discuss. It's true that in quantum theory, if you have a higher derivative term like this q double dot squared that we'll have here, then that is a warning bell, because you have a ghost, and people have grappled with that in various courageous ways. But it presents a problem of ghosts or negative norm or something of that nature. And what I want to say here is it's okay. In the quantum theory, it's a problem, but in the classical case, it's just the usual thing we always have in classical stochastic integrals, because in Brownian motion, this is just the path integral for Brownian motion. There's nothing pathological. There are no ghosts in Brownian motion. Brownian motion is a perfectly well-behaved theory. And the reason that you don't have a ghost is because you get the ghost because you take the theory to be deterministic. You solve for its Hamiltonian, and you find that its Hamiltonian is unbounded from below. But here, the Hamiltonian is just the usual p squared over 2m Hamiltonian. Nothing has changed about the Hamiltonian. We've just allowed for stochasticity. So you find that the Hamiltonian is still bounded from below, and so you don't have any ghosts. Nonetheless, you have these higher derivatives, but it's okay.
Interesting. Okay.
Francesco's got his hand up, I think, or oh, maybe not.
I understand your main idea. Yes, if there are some questions, maybe people can ask just now.
May I ask a question about density matrix? One of previous slides, density matrix with alpha. For me, it's not clear how you deal with coherences. Yes, here. So I understand that diagonal elements of the sigma are related to classical coordinates, but how alpha is formed of diagonal elements?
So it's just that it's so if for a particular classical coordinate, there will be a certain probability of being a 0 and certain probability of having a 1 and a certain amplitude of the off-diagonal element. So the off-diagonal element will depend on where you are in phase space. But yeah, that's all. So if I imagine a Stern-Gerlach, then initially I could have a lot of coherence, and as time goes on, then the off-diagonal elements might decay.
So
alpha, for example,
related. Do I understand correctly that alpha depend on visibility of interference picture in stochastic, the amplitude of stochastic influence?
Well, don't forget, I'm not modifying. Quantum. The quantum particle is still a quantum particle. Still has. So it is the coherence. I can do an interference experiment and look for its visibility. The only thing is that coherence off diagonal element matrix depends on the phase space coordinate. And so here's an example of a Stern-Gerlach experiment. I start off in the plus state, so a superposition of spin up and spin down. The spin of the particle is quantum, but the position of the particle is classical, and so the particle either has a positive, the momentum kind of gets kicks in momentum and goes up, or gets kicked in momentum and go down. And so initially I start off in the plus state, and gradually the coherence goes to 0, and I end up in the 0 state or the 1 state. So the coherence depends, and also the probability of the particle being up or down depends on where I am in phase space.
Okay, thank you.
Can I try to ask my question now? Can you hear me?
Yes.
When we have like fourth derivative terms in classical theories, in gravitational and general relativity, we also have something called the Ostragradsky instability for perturbations. So I imagine, but since you're putting like kind of phenomenologically your stochasticity, it doesn't appear on your Hamiltonian, so you don't have a problem. But the origin of this stochastic motion must be somewhere, and I imagine, like in cosmological settings, all of those kinds of things, perturbations will feel this kind of instability, and they in classical perturbations, will be very problematic to have fourth derivative terms in the gravitational equations of motion.
So I don't think so. So let's discuss that. So here's the Ostrogotsky instability, but let's just start from the beginning to make sure that we're on the same page. So this is just a reminder that in quantum theory, this is a usual quantum path integral where I have the kinetic term, and here our path integral has higher derivatives, but it's classical. So there's it's not imaginary. It doesn't, this is just Brownian. So here again is Brownian motion. I'm giving you the path integral for Brownian motion. It has a higher derivative term, but that just is representing Brownian motion. And you can look up Feynman and Hibbs, and you just see that you have these higher derivative actions for Brownian motion, and there's no problem. This is completely equivalent to the Fokker-Planck equation or the Langevin equation. Let me maybe even go, I don't know if that would be helpful. Would it be helpful to see the Langevin equation, or? I'm not sure.
Excuse me, because if you're supposed to use the anarch with Brownian motion and maybe from the beginning, we have to deal with relativistic system. Somehow, it means that you need to generalize a relativistic Brownian motion. Is correct or not?
It's correct. So
Correct.
let's let's see that. So this, I think, could be the main message, which is that this is the path integral for Brownian motion. We see that we have this q double dot squared. That is this Brownian motion, and I just want to emphasize that higher derivative terms, but it's not pathological. It is just Brownian motion. There's nothing strange about it. It is equivalent to the Fokker-Planck equation. It is equivalent to the Langevin equation. The Hamiltonian is bounded from below. There is no instability. It is just Brownian motion. Here is the quantum system if I have two double derivatives, and that we know from Ostrogotsky has the ghosts. But the reason it has this instability is because in quantum theory, we say, okay, this must have come from a Hamiltonian. Here is the Hamiltonian, and it is bounded from below. On the other hand, in Brownian motion, what do? You say, oh, this is, we don't look for a deterministic Hamiltonian for this action. This is a probabilistic action, and so the Hamiltonian is the same as it was before, but it has this fluctuating term. So the difference is that the Hamiltonian is still bounded from below, but it has fluctuations, like in the Langevin equation, whereas if in the quantum mechanics of the system, you would have this Ostrogotsky instability because the Hamiltonian is bounded from below. So in some sense, this is a key message, because what happens now? So now so I mentioned that we have the equation of motion squared. That's what the action is. So let's take Einstein's equation, square it. We have the r mu nu term and the r squared term. So this, what does this do? It says that you want to satisfy Einstein's equation. This is just the vacuum. We've only done this for the pure gravity case. We have fluctuations essentially around Einstein's equation. And so this action is zero when Einstein's equation is satisfied, but it is, we allow for fluctuations around it. So now you have this r squared term. You can rewrite it, as many of you know, as just an r squared term, a Weyl curvature tensor squared term, and the Gauss-Bonnet term. And what is nice is that this theory is renormalizable. It doesn't have ghosts now because we don't interpret it, because it doesn't correspond to a Hamiltonian, which is bounded from below, unbounded from below. And what's more is that this is actually scale invariant. So what happens is the D2 now actually runs to zero at the short distance scale. So that means that the stochastic fluctuations become weaker on the short distances, and the theory is renormalizable. So that's maybe one headline message for people, which is that if we think of quadratic gravity as instead computing a probability rather than an amplitude, then we find that it's renormalizable without ghosts, and that the running of the coupling constant means that we have very little stochasticity on the short distance scales. Other questions about that?
I have a question. So I think maybe you are talking about the DW, that is the term which is giving ghost, and not the R square term. R square term doesn't introduce any ghost. So it is the Stravinsky theory. Maybe your comment is about DW, not D2.
Yes, I think so.
Okay.
And there's a question from Antonino. Or maybe not.
Yes,
another
Antonina,
question?
please ask your question. Yana Antonina, are you here?
Maybe muted.
No,
I can
no,
take it
no,
at the
he's
end
not
if
on
there's.
mute. He's not on mute.
Maybe
Okay, well,
can proceed. Yeah.
proceed and feel free to interrupt. So I guess you were asking, in some sense, this is the relativistic stochasticity of Brownian motion, right? So I have stochasticity around, well, in this case, it's just that these coefficients should be 0. And so we have stochasticity around Einstein's equation in the pure gravity case, at least. And some renormalizability. Now, when we add matter, things become more complicated, and it's unclear to me what happens with matter because it's not minimally coupled. It's quite a complicated theory.
Sorry, my comment was kind of about that. The Ostrogradski instability in cosmology happens when you couple the background with matter. It doesn't happen alone with just the background. It happens when you have perturbations of matter on a background with unusual terms, fourth derivative terms. You have instability of perturbation in cosmology. In classical background. Nothing to do with ghosts or quantum theory.
Okay.
So
can you hear me now?
Yeah. Yes. Hello. Hello.
Antonino,
Yes,
Antonino, please ask your question. Maybe his microphone does not work. You can also write your question in chat. We can read it.
Okay.
Jonathan, just a small question or comment. I don't know. The thing is, you're mentioning these quadratic terms as fluctuation or GR, but in the context of Stravinsky inflation, during inflation, R square term is the dominant piece. The coefficient is huge. It has to be
That's
there.
right.
Otherwise, you cannot explain the CMB, the density fluctuations. So, yeah, I don't know. Do you agree with this, or do you have a different opinion?
Yeah, so I agree with it, and I think that's what makes this attractive, because actually it is notice that there is no R term here.
Okay.
So I mean, you expect to get an R term induced, but the dominant term is the R squared term, and that is, for some people that's a bit puzzling, because they will say, oh, well, where is the Einstein-Hilbert term? Well, it's not there because this is an equation of motion squared, and so the dominant thing is the R squared term. So I feel like this gives a plausible motivation for Stravinsky inflation, because in this theory, the R squared has to be very large. It dwarfs the R term, and it is also the case that and one doesn't have the issue of negative norm or ghosts or whatever. Someone just said previously that they think that is only if you add matter, but I think the problem of ghosts or negative norm comes about, or tachyons, they come about in just the pure gravity theory. So I'm not sure what is meant by them arising only when you couple to matter. I think they are in the pure gravity theory.
I was not talking about ghosts, but the Ostrogradsky instability in classical cosmology, but go ahead.
Okay. Okay, so I think we're at the quarter after mark. I can end with some final slide, or I can talk a little about this anomalous contribution.
By the way, how many time do we need to go to conclusion? Of course, we had a lot of discussion.
We did,
and
yes.
we started 5 minutes later, but also taking into account always, we already have 1 hour, 5 minutes. So how much time you need to go to conclusion, if it's possible? Just tell your answer, and then we will decide.
Yeah, so my conclusion is about is 5 minutes. I could
okay, 5-10 minutes is okay, I think. Okay, please go ahead.
So what I want to say about this is that so the thing I'll say about, say, this action in terms of how we understand it is that this represents when the action is zero, that's the deterministic equations, but you're allowed fluctuations from this. And it's interesting to think about, these stochastic fluctuations, do they, what do they look like in cosmology or on the scale of galaxies? And we're actually going to put out a paper, I think, in a week, where we are looking. I think this is the more interesting one, where you look at the stochastic fluctuations produced during the expansion of the universe. And what we find is that there's this, they look like matter in some sense. You get a anomalous contributions to this path integral, which look a lot like matter. And for those people that are interested in quadratic gravity, that one way of thinking about it is that, what's a good way of thinking about it? I guess maybe the best way of thinking about it is a little bit like in Brownian motion. So in Brownian motion, if I have a particle and I start it, say, at x equals 0, and then I let it evolve, it will not just sit there at the origin. It'll either drift to the right or drift to the left. And so if I look at some later time, I will find that it has this distribution around x equals 0, but it will have this width to it. Now, if I have a wall, like if I have a potential, then not only will there be stochastic fluctuations, but the stochastic fluctuations will push the particle away from its mean value. And we essentially find this effect in the path integral, where we get pushed away from the mean value of the deterministic equations of motion, and we get these anomalous contributions which push us off GR. And we find, I would say, very strong evidence that these lead to contributions which look like both a cosmological constant and which look like, in cosmology, which look like a phantom form of cold dark matter. And hopefully the paper will be out in later this week. We have but maybe just to say that, just like in quadratic gravity, if you solve for the action, you get variations away from Einstein's equation. Here, if you solve, like in quadratic gravity, if you solve for what you think are the equations of motion, well, what they actually represent is stochastic contributions away from the deterministic equations of motion. So let me just end with a final 2 slides. So I presented this theory, and I want to say that there are some challenges which remain. For example, we know that it's renormalizable in the pure gravity degrees of freedom, but when one accounts for matter, then it's unclear what happens. There is a bit of a tension between, which seems to be resolved, but we haven't proven it, but there seems to be a tension between the theory being normalizable and it being something which is called completely positive trace preserving. And so there's a few, I would say, tensions which exist within the theory. And these, I think, are interesting what I want to say. I believe these are resolved, but not always proofs of these. So, for example, the thing I would highlight, for example, is this tension between complete positivity and normalizability. So let me just end with the kind of main summary. There's this question, which I think is an interesting question, which is whether space-time is quantum or classical or something else. I don't have any idea what the answer is. But what I want to say is that it could be. I think that seems to be clear because we have this consistent theory. If we imagine that it is, then we have a number of interesting consequences. For example, the measurement postulate of quantum theory is not needed because you automatically get collapse of the wave function. The theory becomes renormalizable without ghosts. It's experimentally testable and could account for dark matter or dark energy. And so with that, I'd like to thank you for your attention.
Irina, you're muted.
I'm you. Oh, excuse me. Let me repeat. Jonathan, thank you very much for your very interesting talk. You presented a new idea. We have to think about this. At least I suppose I will think more. I like this idea because this is for me, it is something really new. Of course, there are some questions, there are a lot of questions about this, and maybe we can discuss some of them now. Please, question. If somebody can read the Antonio chart, because I have a very small iPad with me, and I have two small letters. Could you please just...
Can I read, Luca, you want to read?
Yes, yes.
Please,
yes, please.
So the question is about adding a stochastic noise to a theory of gravity induces a breakdown of its symmetries. What kind of probability distribution do you expect to have around the equilibrium configurations, that is, solution of Einstein equations? That is first question.
So do you mean that you're worried that if I have stochasticity, I will break diff invariance? Is this what you're worried about?
Well, it seems I'm reading from Antonio's question.
Yes.
Yeah, this is what I understand. Maybe
I see.
Yes, that's yes.
So this was this tension that I mentioned, and so I guess what I can say is that we have a action which is manifestly diff invariant, but we haven't proved that it satisfies a certain property called complete positivity. So that's something that we are still trying to prove. And so in that sense, I can't tell you that everything is for sure okay. However, we have, for example, let me give an example. So we have a theory of Nordstrom gravity where everything we can prove complete positivity. The theory is diff invariant, although because it's Nordstrom gravity, it has a flat background. It has a background. And so but it shows that at least in principle, you can have diff invariance and stochasticity and be consistent with quantum theory. So I don't think it's true that you break the gauge, but it is certainly true that understanding how diff invariance works in a stochastic theory is not straightforward, and that's in part because the generator of diffeomorphisms is no longer no longer the Hamiltonian constraint.
So, well, a response from Antonio for your explanation is that the Langevin equation induces fluctuations over the symmetry constraints, which are the part of the equations of motion. This was pointed out by Rumpf in 1986.
Sorry, can you say that again? Ruin 86 says what?
Yeah, well, I may be pronouncing the name incorrectly. It's Rumpf from 86. Said that Langevin equation induces fluctuations over the symmetry constraints.
So it is true that you have, I would just say it like this maybe. It is true that if I look at, say, the Hamiltonian density, that it has a stochastic contribution. And so when you say, what do I mean by the constraint equation? it's a tricky thing. And so I would say what the constraint equation is, and maybe this is what you're saying, is that it is the Hamiltonian plus the stochastic part, which is the Hamiltonian constraint. And so when you actually try and see if the theory is different variant, what you find is that you get a very different algebroid than you do in the deterministic case. I'm not sure if this is saying what you're saying in a different way, but I would be interested in this reference if you have it. But there's been a lot of discussion back and forth on whether, for example, you can have stochasticity or decoherence and still maintain Lorentz invariance, and the answer is certainly yes. I can give you a Lorentz invariant theory which has noise, so that's not a problem. But it is also true that the generators are different in the stochastic case in comparison to the deterministic case.
Okay.
Okay. More questions, please?
Can I ask, maybe Irina, start with?
Yes, please.
Okay. So, Jonathan, thank you very much for the talk, first of all. It was very interesting. I do have several questions, but maybe I will ask just a couple of them. So the first is related to this quadratic action that you get. So yeah, I understand that basically what you're doing, you're just squaring the Einstein equation following the Brownian motion example, basically. So as you said, the physical Hamiltonian in that case should still be the same as the one in GR.
Yes, right.
So this seems to imply then that basically these R square terms, they are not introducing any new degree of freedom. You still have the same degrees of freedom in GR. Is that true?
It is true and not true. So this is like in Brownian motion. So in Brownian motion, let me give an example. In Brownian motion, if you now add noise, you are not really introducing physically any new degrees of freedom, but in some sense, you have a bit more freedom because I can, for example, tell you it becomes relevant at t equals 0, what is the position of the particle, the momentum of the particle, but also its acceleration, because its acceleration is no longer uniquely determined by its position and momentum. So in some sense, there's more freedom, although these are not additional degrees of freedom, if that makes sense.
Yeah, so basically you're modifying the dynamics, but still you do not have new propagating degrees of freedom.
That's right. That's right.
Okay.
Well, again, is it's that is true and not true. So, for example, another example is like in quadratic gravity, you both have the scalar and the tensor mode, right? And so here you have this scalar mode, which isn't in the deterministic theory, and it's not really a new degree of freedom, but it's a result of, well, in some sense it is, because the fact that you have these metric fluctuations mean that you have more degrees of freedom.
So somehow, I mean, you should see in some effective Hamiltonian these additional fluctuations, right, due to these extra degrees of freedom.
Yeah, well,
because somehow
you see these fluctuations, and one way of thinking about the fluctuations is that these are somehow give you additional degrees of freedom, because if you need more information to describe your system. Maybe that's a way of saying it. In a deterministic
I agree
theory,
with that. Yeah.
Yes, maybe that's a way of saying it.
Mm-hmm. Because anyway, although you're not quantizing GR, through your procedure, you're introducing anyway a new fundamental constant that is this D2, right? That is in front of the action.
Yes.
So somehow you have a new free parameter, which maybe is not related to, let's say, new masses, because you just have a purely quadratic Lagrange in the end. So there will be some new parameter in your theory that is purely related to this extra information due to the Brownian stochasticity that you have in your problem.
Yeah, so there's it's a dimensionless parameter which tells you how large the fluctuations are. And this, I guess, as in QCD, you expect to generate a length scale at which, so effectively one expects this. So you get this additional dimensionless coupling constant with probably a new length scale introduced by dimensional transmutation.
I see. And okay, so at some point towards the end, I just got confused a bit with the language, maybe because, of course, you have this quadratic Lagrangian where you have these dimensionless coefficients in front of the quadratic terms, but still your theory is classical. So in a certain sense, you do not have any running of these parameters, right? Because you're not really matching.
Sorry, why do you think that they might not be?
Because if you just pure gravity, you will not quantize this pure gravity.
Well, so just like as in, so if I have a classical field theory, I still need, you still have to renormalize it. In other words, if I start computing things with this action, it is just an action. I mean, if I want to compute a probability of a certain transition happening, then I compute it just like I would in quadratic gravity, say. So, I have, I need to worry about whether the theory is renormalizable, and the coupling constants run just as in a quantum theory. So there's not much difference, except that everything is I'm computing probabilities rather than amplitude. So the interpretation of what you're doing, in other words, it looks very much like quadratic gravity, but and the coupling constant runs and it's renormalizable, but the interpretation is different. I'm computing a probability of a transition, not an amplitude.
Okay.
Okay. Maybe we can go to the next. Yeah. Okay, sorry. Francisca.
No, please go.
Francisca, could you please ask your question just now?
Yeah. Very, very quickly. If you don't have the linear term in your classical limit for gravity, wouldn't that be a problem for usual predictions of general relativity? And secondly, just to make the two questions at once, if you said something that at small distances, these corrections are not important, is that correct? The stochasticity is not important, and it is important at larger distance. Is that something correct?
Okay, so
my question would be, at the early universe, these R2 term is very important, and so the stochasticity must be important, right?
So the stochasticity is required. So you definitely need stochasticity on the length scales that we observe superpositions, because it's the stochasticity on that length scale is what prevents what allows interference patterns to happen, right? So on that length scale, so let me just say the things I know first. So I know that on that length scale we require stochasticity, which we can bound from experiments. Because the coupling constant runs and the d2 goes to 0, it means that on the short distances, there's not, the stochasticity gets smaller. Your question now is about on the cosmological, in the cosmological setting, and there we also expect them to be significant. So,
it's significant.
Yes.
Even at small distances.
Sorry?
I mean the cosmological setting at the very early universe. So I'm talking about small distances.
That's right. So just like as inflation, so inflation, I have my quantum fluctuations, and I believe that is what has expanded to seed structure formation. You expect these to behave very similarly.
So that's the end of my question. So the origin of structure formation, the perturbations would come from the stochastic fields.
So yes, that is in some sense the idea.
Just a comment. That will be a very big challenge to reproduce the whole perturbation, cosmological perturbation history with a whole different starts and a whole different stochastic. I don't know the rules that you have to follow to get reproduce the scalar spectrum. How would you do that? I can't imagine how you do that.
Yeah, so this is some joint work with Andrew Ponson and Emanuele Panella, and we find that it looks like cold dark matter, but we in terms of there's some caveats because there's some things we don't understand. So, for example, we might be worried that it gives too much variation in the amount of what looks like cold dark matter. So in this sense, we at this point don't know if it can reproduce all the phenomenology, but we can say that on average, at least, it does seem to.
Thank you.
Okay, I saw questions from Savidi, but he's not here, I guess. George, are you here? No. If he's not here, okay. Next questions from, I see from Shravan. Shravan, please ask your question.
Hi, Jonathan. So thanks for the very nice talk, and I have several questions and also share some opinion on things what I'm doing, but I will write to you separately. So I want to restrict to one specific question here in the context of quantum field theory in curved spacetime. So the point is, well, gravity is classical. That's what you're treating, and quantum mechanics. So there is a conundrum here, concept of time. Time role in quantum theory is a parameter. Okay, in the gravity, it is related to dynamics. But of course, for example, if you talk about universe, expanding universe, there is a scale factor, which is the clock. That's why in the Wheeler-DeWitt equation, time does not appear explicitly, only the scale factor appears. So I'm wondering, how do you, in your formalism, how do you deal with it? Do you separate the concept of times in gravity and quantum mechanics, or not?
I mean, this issue of no. So I mean, so this issue of the problem of time is very particular to the quantum theory, because in the quantum theory, in some sense, if you're going to satisfy the Hamiltonian constraint, then in some sense, it's like the Hamiltonian is zero, and if the Hamiltonian is zero, then you know, then you are timeless in some sense. You don't evolve. So in the classical case, that's not a problem. You know, my Hamiltonian can be zero, and I can still evolve just as I would in classical GR. There's no problem with the evolution law. Now you still want the theory to be reparameterization invariant, so you still expect that symmetry to hold. Whether you know, we have proven that there's one version, the path integral is diff invariant, but you know, we have not proven that theory is completely positive. We have the we have the master equation approach. In the master equation approach, we know that it's completely positive, but we haven't proven that it's diff invariant. So that's this kind of tension that still exists, which we haven't yet proven.
Just to confirm, so you started your talk with the Wheeler-DeWitt equation in one of the initial slides. Yeah. So, but you do not, because you did think that in your framework, okay, you try to fix it gravity to be classical. That means you do not worry about the Wheeler-DeWitt equation and problem of time in some sense. Am I correct?
That's correct.
Okay, thanks.
More questions, please.
I have one. I'm actually signed up as Andrew Little. I'm clearly not Andrew. I'm sorry. We kind of, it's in our household of, I'm Marina.
Okay. Marina.
I couldn't hear the whole talk because I had to sidebar onto another Zoom, but I did hear this. I've been very interested in your work, and I did hear the description of the path integral, in which you alluded to a sense of Brownian motion, and also referred, if I believe, briefly to both Lars Onsager, and gosh, what's the name of the guy?
Matchloop.
No, the 1969. Oh,
Matchloop.
Can you repeat?
Onsager Matchloop?
No, the person that defined the butterfly effect. Oh gosh, I'm so bad with names. 1963. Let me see if I can call Andrew. Just 1 second.
I mean, but sorry, what was the question?
I will get to the question if I. What is the name of the 1969 guy from Oxford? the person that did the real butterfly effect. Lorentz. Jesus, I'm really bad with names. Okay, I'm good. I'm not sure he's from Oxford. He's from Oxford, of course he's from Oxford. Anyway, so the question is, there is work that I wanted to bring to your attention, because when the way your work is being referred outside in other seminars is a full continuum description of quantum gravity, and Onsager and Lorentz have a very good work referring to both Brownian motion, but a more recent notion of these, what they call stochastic spontaneity, or no, spontaneous stochasticity. There is these Rev letters worked recently just by the Johns Hopkins team, and also by Tim Palmer, that questioned the continuum even in the classic domain. And it seemed to me that as you were averaging over trajectories using a sort of Brownian motion, you were diverging from the absolute continuum, possibly parallel to the ideas of Onsager and Lorentz in this, that is away from the continuum, possibly to the fractal regime, or basically more onto violations of the continuum that are being observed today, even in classical mechanics, in the Navier-Stokes equation, both in the Euler description and the Lagrange description. It's really very relevant work in classical mechanics, and that's where I am going with my quantum gravity. I'm looking for what's happening. What is the community finding in the continuum already in the classical regime that are sort of violations of the continuum? And so the question was, are you thinking along those lines, that a continuum sort of becomes along the lines of what Onsager defended, and also Lorentz?
I mean, right. I'm not so familiar with of those works, but here we're treating phase space, both the phase space and the manifold, the spacetime manifold, as continuous.
Pure, in the
yeah,
absolute sense.
That's right. Yeah.
Oh, okay. All right.
Yeah.
So that's good.
Yeah.
Good.
I mean,
Okay. So, okay, more questions, please. I don't see more questions. If there is no
I don't know if you can hear me now.
Yes.
Okay, great.
Okay.
That's great. So no, I mean, I want to come back to the point about the probability distribution, because I mean, you were saying before that you have a Brownian motion, but I mean, that's the point that I don't completely understand, because I mean, at least in some cases, if you consider a Langevin equation with the stochastic noise added to gravity, to classical gravity, then in that case, for sure, I mean, in some cases, like take into account, for instance, radial spherical symmetric space-time solution, you will not have that the fluctuations are described or accordingly to a Brownian motion, but rather they fulfill Kardar-Parisi-Young probability distribution. So just want to understand why, I mean, you're emphasizing the Brownian motion. Maybe there's something that I'm missing.
No, so this is purely pedagogical in the sense of, if I'm making an analogy with the path integral that we get, that it's analogous to Brownian motion. I'm not making
analogous. So it means that, I mean, it's you open the door to the fact that there could be some other probability distribution outside of the equilibrium, out of the equilibrium.
Yeah, I mean, well, it depends how you describe Brownian motion. So, I mean, so we would normally, so in Brownian motion, you sometimes describe it as a white noise process, but I guess we would, there are various technical details in terms of making sure that the distribution is continuous in terms of a Wiener process, and then the actual, I guess at the moment we are taking the path integral as fundamental, and then that determines for you what the
yes,
from that you can determine what the 2 point. Yeah, from that you can determine the 2-point function, and that in some sense is what is gives you the theory.
If you take the path integral as fundamental, and for instance you follow the Parisi Wu, let's say seminal paper.
Parisi maybe.
Sorry, what?
Are you sure that is Parisi Wu or Parisi Surlus maybe? No. No,
it's Parisi Wu.
Okay.
The paper that I'm quoting is Parisi Wu 1980, Scienza Cinica. Okay. So, and I mean, that is a paper about stochastic quantization of a field, and they describe stochastic quantization of gauge field in that case. And they describe indeed, in that case, out of equilibrium with respect to the constraints that are the constraints of gravity.
Yeah, I'm not sure the relationship with stochastic quantization, which is a kind of a different thing. I guess there's a lot of these different path integrals which are related, but I guess there's this Martin-Seger-Rose one, which is usually what people look to in terms of a classical stochastic theory, and I'm not sure what its relationship is with Parisi Wu, but I think Irina is correct in that there is also this paper by Parisi Sulas, which is, my recollection is also that it may be more relevant because they talk about, my recollection is that they worry about such things as the normalization, which looks a bit like the things that we have to worry about. So,
I mean, for sure, it's the two paper, for sure, I mean, the other paper will be also important in a certain sense, but I mean, the Parisi Wu is comes later and is applied directly to gauge fields. So, and the reason why I was quoting it is because it's connected to the question that I was addressing earlier about indeed, I mean, it's the symmetries, so breaking down the symmetries. So if you consider just a Langevin equation, so right now, I mean, we're doing anything else than applying, I mean, statistical mechanics methods. So you're fluctuating above the constraints, and the constraints are imposing part of the equation of motion, even for gravity, as we know. So in this case, when you are not at equilibrium, so when you consider the stochastic noise, you're not closing the constraints algebra. Super constraints algebra. So in this case, you're breaking the diffeomorphism.
Well, no. So I would disagree with that, because what you actually have to look at is the point is that the generator of spatial diffeomorphisms is just is the same, but the generator of time-like diffeomorphisms is different. It's given by the Fokker-Planck equation itself, or the equivalent to the Fokker-Planck equation. So you need to be careful.
What do you mean? What do you mean? Well, sorry, if you consider Langevin equation for gravity, for the gravitational field, and you do an Hamiltonian formulation in ADM variable, you will have a stochastic Langevin equation for the lapse function and the one for the shift vector. The one for the lapse function, of course, involve the super Hamiltonian, which is the generator of the time reparamerization. The one for the shift vector involve the generator for the space diffeomorphism. Both of them are out of equilibrium.
I think what I would say is that the generator of spatial diffeomorphisms is the same. That doesn't change, because if I move spatially, you don't get decoherence or stochasticity in space. You get this in time. And so, on the other hand, the generator
Sorry,
of...
what do you mean it doesn't change? It depends where you start from. I'm saying that if you start from a Langevin equation for the metric field, for dimensional metric field, space-time, in that case, you get, in IDM formulation, two different Langevin equation, one for the lapse function, involving the lapse function, and then involving basically out of equilibrium super Hamiltonian, and another one which involve Langevin equation for the shift vector. The one for the shift vector, then in the non-relativistic limit, converge toward, reproduce the Navier-Stokes equation, but with an intermittent force term, which indeed, it's is a deformation of the Navier-Stokes equation. But in both cases, you are out of equilibrium. In both cases, you make dynamic of the Lagrangian multiplier. So in both cases, you break both the generators of the diffeomorphism.
I can give you. Maybe this is getting a bit technical for maybe there's something to talk about after. But I can give for you for example, a path integral which is manifestly covariant, and so is diff invariant. Understanding it in terms of the generator of spatial and temporal diffeomorphisms is subtle, and what we find is that I guess I feel like there's some disagreement here
but this is exactly no, of course, but this is exactly my point. That's why I was tracing back to the paper not by Parisi-Surla, but the paper by Parisi-Wu, because in the paper by Parisi-Wu, in order to consider the degree of ambiguity and so on, they put the system out of equilibrium, so they break explicitly the symmetries. That in that case, that they consider is the gauge symmetries for gauge theories. And what Rumpf did, they was just considering basically the same for gravity. So it breaks the gauge symmetry of gravity, so diffeomorphism, and you break all of them. Of course, you can choose a stochastic noise, which is with an ad hoc ansatz, such that you don't put the noise on the 0,0 component of the Einstein equation, or 0,0 the one that after a combine to the lapse function. And of course, if you do this specific choice of the stochastic noise, I agree with you, but this is very specific.
Yeah, so I feel like there's a lot to unpick there. I guess I would say that if you choose noise like that, where you still respect the constraints, that will not be diff invariant, and that one can immediately see. So I wrote a paper with Zach Weller-Davies on the constraints of this theory, which maybe are helpful, because you see that the constraint structure changes quite a bit, and we talk about the algebroid of constraints. I think what I can say is that it's this thing I said before, that there is a tension between diff invariance and complete positivity, and we have a theory which is diff invariant, but we cannot prove it's completely positive, and a theory which is completely positive, we haven't yet proved it's diff invariant. So there is an open question, but I find that most of the So I just would be wary about some of the I would say the vast majority of the literature, because I think there's a number of subtleties which one needs to take into account when understanding
I agree with you that there are different opinions in a certain sense, and this I agree completely with you. In the minute in which you add the stochastic noise, in a way which is not covariant. It's a point which is very evident. The point that I was making before was ad absurdum point. The fact that this choice that would be very peculiar is indeed inconsistent. So there is no choice that only allows you to break space diffeomorphism, but not time renormalization. You have to break everything basically.
Right. So I don't think that. I think there is noise you can add, which is diff invariant. If you add scalar noise, then that is a diff invariant form of noise.
But scalar noise. Sorry, how do you define scalar noise? With the ansatz of a scalar times tensor, times metric, because that noise break both spatial diffeomorphism and time renormalization. What do you mean for scalar noise? Sorry.
I think just I think just scalar noise. I think one has to be careful about what one means about diff invariance, because all you care about here is that the probabilities of certain trajectories are maintained after a diffeomorphism. So you can have a particular realization.
But the
which looks like it breaks
probability would be maintained only at equilibrium. Maintain, I mean, it's by maintaining which sense? I mean, but that's why I was referring to the Langevin equation. I mean, and to the Parisi-Wu, let's say, approach, because there, I mean, it's there are two kind of let's say time that you have to consider. There is the proper time and there is the thermal time. The two actually are also related, but there are two different concepts. And there is even a concept of dynamics, which is differently induced by the fact that you have a thermal time and the fact that, I mean, you have a Lagrangian multiplier that are no any longer Lagrangian multiplier out of equilibrium with respect to the thermal time.
Right. I mean, maybe I feel like we could give a whole talk and a discussion on this one particular topic, and it's quite technical.
Oh yeah, of course. I mean, we can continue privately for sure. I mean, anyway. I mean, your talk is very interesting.
Right. So I'm happy to stay after we've closed the session and continue to discuss it.
I am in Shanghai. It's already midnight.
Okay.
So, but I'm very happy to write you privately, and we can find a time in which both of us can discuss.
Right. And I would recommend this paper with Zach Weller-Davies on the constraints of these stochastic theories, because I think that gives a sense of kind of why things are different.
I also would like to recommend a paper that I wrote with Matteo Lulli, which is about the stochastic Ricci flow, in which I specify most part of the things that I've been just spelling out now.
Good.
Okay, maybe we have to finish the discussion between two people. But in any case,
difficult to break in there. Yeah.
Yes. In any case, I don't see more questions, and we are almost 2 hours at this seminar. So let's thank the speaker again for very interesting talk. Really, for me, it was very interesting.
Thanks very much, everyone.
Thank you very much. And don't forget to send us maybe your transparencies, okay?
Will do. I'll do that. Great.
And I hope you are not against